Hello everyone, and welcome to my first official developmental video for my upcoming Voxel game, Voxuloris. So this will be the first of many videos discussing the development of the game, everything from code to implementation, to how I've gone about implementing certain features, pretty much anything that relates to the game itself. So what is Voxuloris? Well, Voxuloris is a 3D multiplayer voxel game heavily inspired by Minecraft, built within the Unity 6 game engine. Why am I making this? Well, I sought to challenge myself and learn in the fields of programming, 3D modeling, texturing, game design, and computer networking. I also wanted to make a game that I myself could really enjoy and play with other people. By making this a standalone game instead of a Minecraft mod, I have full creative and structural control over every aspect. In terms of features, going off Minecraft as a baseline, I aim to have crafting and progression be a lot more intricate and linear than what Minecraft offers. Survival will have a lot more critical variables for the player to keep track of. Worlds are finite, with far greater vertical height, and potentially, down the road, even some small-scale automation. Some other notable games I'm taking inspiration from are the Blockheads, Terraria, Starbound, and a few Minecraft mods, such as Buildcraft, Industrialcraft, Thermal Expansion, Forestry, Tinker's Construct, The Aether, Terraformacraft, and many more. With all that being said, let's get into some details. My first step was determining the physical dimensions and subdivisions for my world. In Minecraft, there are 3 dimensions, with the world being procedurally generated along the positive and negative X and Z axis. The world is then split into subsections called regions. Regions are divided into 32 by 32 chunks. Chunks are then divided by 16 by 384 by 16 blocks. When exploring, Minecraft can dynamically generate new chunks and then create or update the corresponding region file that said chunk would map to. Worlds, while seemingly appearing to be infinite, are not. By default, a world boundary is placed at 30 million blocks on both the X and Z axis, and even if the border is removed, the game will eventually start breaking down in the hundreds of millions of blocks due to floating point precision issues along with other things. In Voxuloris, worlds are exactly 8,192 by 8,192 by 8,192 blocks. The world is aligned to exist only in the positive range for the XYZ axis. My rationale for the world size is mostly due to floating point precision issues imposed by how Unity handles rendering. I am aware of possible solutions to this problem, however in this stage of development I do not wish to tackle them. Neither do I feel compelled to expand the world for gameplay reasons, as I believe proper world structure, plus additional dimensions, will give even multiple players plenty of terrain to explore and resources to gather. As for how things are divided, the world is split into regions. Each region is 128 by 128 by 128 blocks, making the world exactly 64 regions wide. Similar to Minecraft, each region corresponds to a separate file when saved. However, unlike Minecraft, regions are not divided into chunks server-side. Regions themselves are the smallest division of voxel data the server works with. When fresh terrain is needed, the game will generate an entire new region worth of terrain. This simplifies the loading, saving, generation of voxel data, since all regions contain the exact same number of blocks within them. Structuring voxel data in this way allows multi-threading to be easily integrated. Each thread can be given a separate region to save, load, or generate, without needing to read or write to some larger file or shared data structure. To improve performance, I have heavily taken advantage of object pooling in order to avoid allocating hundreds of megabytes of memory every time a region is loaded or generated. This does come at some costs, such as a maximum amount of loaded regions at once and slightly less convenient code implementation, but with the benefit that I can generate hundreds of gigabytes worth of terrain for hours without significant memory leaks. My second step was figuring out exactly what format voxel data should be in for when regions are loaded or saved from disk or being sent over the network. This was profoundly tricky, as it involved many variables and constraints that limited my options. Storing block data in the exact same way as it's represented in memory would result in massive file sizes, increasing the time it takes to load and save from storage, and from a networking standpoint, it would require an insane amount of bandwidth to sync with clients. I needed to come up with a solution that could dynamically compress voxel data, along with encoding and decoding that could be used for both region files and network packets, all without excessive heap allocation while being multi-threading safe. Without going too deep into my implementation, I went with a combination of run length encoding plus C#'s built-in compression library. In combination, these tools could compress the size of a region file or a voxel data packet by a factor of anywhere from 2 to 1000, although on average I saw about 8 to 20x size reduction. My third step was figuring out exactly how to send voxel data to clients. The networking library of choice was NGO, also known as Netcode for Game Objects, which is part of Unity's official networking solution. My reasoning for choosing NGO is that it's designed exclusively for Unity and has great support and integration for Unity projects, along with constant updates, making it stable and functional even for the newer versions of Unity 6. With that set in place, I then needed a system that would dynamically sync voxel data with connected clients. In order to explain further, I must explain a critical design decision I made regarding how voxel data is structured, server versus client. From the start of the project, I decided that multiplayer functionality would take complete and utter priority and would be the sole focus, meaning there would be no single player. This would allow me to architecturally structure things around a strict server and client setup, meaning a dedicated server build and a dedicated client build. Due to this forced separation, each build has a different way of handling voxel data, since each has a different set of objectives. The server must store the true state of voxels and perform logic that can mutate their state, while the clients just need to represent what voxel data they receive from the server. Now, while regions are the smallest divisible unit of voxel data server-side, when it comes to sending voxel data to clients, regions are divided into 8x8x8 segments, exactly being 16x16x16 blocks. Trying to sync an entire region in one massive data packet wouldn't be practical, given the sheer size that packet would be, even if the voxel data was hyper-compressed, meaning we have to send voxel data into smaller segments. Client-side, however, voxel data is represented in chunks, with each segment corresponding to a chunk. I have set a universal render distance of 5 segments, which would correspond to 5 chunks in each direction of the player. This is to standardize how much voxel data is being sent to each client, along with how many regions a player's segment render distance would overlap with. By dynamically updating a list, I can skip unnecessarily sending the same unmodified segment twice to the client, reducing the amount of data being sent significantly. This is especially useful when the client moves around frequently, as chances are, unless they are traveling extremely quickly, segments that would be relevant according to the client's old position would mostly still be relevant to the client's new position. In addition, each client server side has 2 queues: low priority for unchanging segments that get sent as the player explores, and high priority segments that are actively being modified. This separation of high and low priorities ensures that changes in the voxels are reflected as soon as possible on all relevant clients, over segments that are not actively being changed. The encoding of segments itself is performed on additional threads on the server, leaving the main thread to just wait for freshly compressed and encoded segments to then send out. Once the segment arrives on the client, additional threads decode the segment and construct a chunk's raw mesh data, which is then spoon-fed back to the client's main thread to apply. On average, each chunk takes around 50 to 500 microseconds on the main thread to rebuild. By limiting how many chunks can be rebuilt in one frame, I can avoid horrible random freezing caused by too many chunks rebuilding at once. I have made some optimizations for the rendering itself, such as not rendering every face on every block, only blocks that are exposed to air have geometry. However, a lot more could be done in the future. With the core foundations of the game in place, I needed to move on to my next set of challenges. The following challenges included procedural terrain generation, structure generation, block updates, block ticks, player inventories, crafting and workbench logic, and animation systems. I won't go into too much detail with these systems, as they deserve their own standalone video, but I will briefly summarize each. For terrain generation, I can utilize Perlin noise. Passing in a voxel's coordinates into a Perlin noise function, and then mapping the output noise value to a certain block type, I'm able to create terrain that is both random, but also coherent. As for block updates, anytime a block is modified, we flag its neighbors to receive an update. Every few game ticks, we cycle through a certain amount of the flagged blocks and perform various logic depending on the block type. I have an arbitrary limit for the number of blocks that can update at once to ensure the server doesn't spend more than 5 to 7 milliseconds processing. Additionally, the server can queue up to 2 million blocks of updates before hitting a limit. To prevent the same block from being flagged more than once for an update, each region has an array of bytes, with each bit in those bytes representing if a block has already been flagged for an update or not. By using bitwise logic, I can derive the exact bit for any given block in a region, allowing me to easily check if a block has been flagged or not. Block ticks, similar to block updates, are relatively simple. Each tick, roughly 1,000 blocks, are randomly selected from each active region, and depending on the block type, different logic is run. For leaf blocks, it's checking if it should decay or not. For grass, it's if it should spread and wear, and for saplings, it's if it should grow. Player inventories, among a lot of things, require that each player can be easily identified. Using Unity authentication, each player is given a unique identity, which can then be used by the server to keep track of what players are recognized and have data. Crafting is dictionary-based, where the layout of items in a 3x3 grid along with a workbench type and tier is used as a key, with the resulting product and quantity being the value. Blocks such as the furnace and chest are extremely complicated. Unlike regular voxels, they contain additional information and cannot be encoded and decoded in the same way. In fact, they have an entire dedicated section within a region file to represent them. When syncing chests and furnaces with clients, I just send their underlying block type as part of whatever segment they happen to fall into. Their item content is sent separately. Given the voxel nature of the game, I didn't need advanced animations, so I decided to create my own primitive animation system. My current implementation is that each unique animation is hard-coded to consist of 8 frames. Each frame can then be interpolated, allowing for a variable refresh rate. With all that being said, there are still a few more topics that I could discuss, such as dropped items, mobs, and physics. However, to keep this video from being too long, I will be saving those topics for another day. Stay tuned for more in-depth developmental videos. I will continue to post my shorter, mostly unedited sneak peek videos as I implement more features. I have never made a video like this before. This is the first time I've ever edited something this long, so let me know what you think. A lot of the icons in this video were made in MS Paint, so take that what you will. But if you made it this far, thank you for watching and have a good rest of your day.